Okay, hello, welcome guys. Welcome to this section. Unsupervised learning, dimensionally reduction. So in this first subsection, principal component analysis. Like principal component analysis is a dimensionally reduction technique that transforms a high dimensional data set into a lower dimensional space. So this is almost same with our this. So almost same with our PCA, but in this principal component analysis, so dimensionally reduction technique that transform in a high dimensional dataset into a lower dimensional space. It achieved by identifying direction principal component that maximize variance in the data. So for this maximization, principal component analysis identify direction where data varies the most. Principal component are orthogonal or uncorrelated to each other and dimensionally reduction. So reduce the number of features while retaining most of the information. So we will use the one dataset for demonstration. It contains certain feature describing one characteristic. So if you can see in our actually we already covered in our previous video. We learned about dimensional reduction in principal component analysis. So there's too much variable, and then they change into just a few variable. We use the data in wine, so we importing the library and data set. So maybe in here. Okay, so maybe we learn using this simple component analysis. So in here we make a text in here. So step 1, we will use the wine dataset. So the dataset contains certain features and 3 wine classes. So the principal component analysis help reduce this feature to 2 or 3 dimensions for easier visualization and analysis. Right, so there's a certain feature, but principal component analysis help this feature to 2 or 3 dimension for easier visualization and analysis. So yeah, these certain features make in 2 or 3 dimension. So we try to data pre-processing first. So feature must be standardized before applying principal component analysis to ensure equal weight for all dimension. Right, so we use standardized the data, standard scalar and scalar fit transforms, and we applying the principal component, and then we want to visualization the PCA result. Right, so we try to applying principal component analysis. So in here, principal component analysis transforms the dataset into principal component ranked by explained variance. So we use this as a component is 2. So we want to PC1 and principal component 2. The df is target is y. Right, so explain variance ratio is just the variance ratio. So the exponent variance ratio indicates the proportion of variance captured by each principal component. Higher value means more information is retained. So the higher more value mean information is retained. So we try to do the visualization also. So the visualization in here, like we visualize the transform dataset into this space using the first two principal components. So we get the PC1 and PC2, and who is target, and then data di PCA-DF and palette set and PCA wine dataset. So the cluster in the scatter plot represents different wine classes. Basically, I separate them based on the variance. So you can see like this is the variance, but the principal component analysis separates them based on the variance. So this is the first, the cluster 0 and the cluster 1 and the cluster 2. So this is really a simple explanation using wine dataset. So they make the cluster based on the principal component analysis. They make just two of the variables. So if you want to check in here, we can use PCA-DF head. So we want to check like this, right? So this is the data PC1 and PC2, and then the target. But in here we just we have in like this, right? So this certain feature 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 feature, and they transforms into two feature, right? So they transforms into just 2 or 3 features. So this is the principal component analysis concept. So help reduce these certain features into 2 or 3 dimension for easier visualization and analysis. So yeah, you just make this simple using principal component analysis, and you visualize them. So you get the cluster based on the data, and then you want to evaluating the PCA performance. So the cumulative explained variance, we determine how many components are needed to return a specific amount of variance. So we compute cumulative explained variance using the PCA. So you can check library PCA is in here. Scalar decomposition, import PCA like this. Okay, so this is the library for import the principal component analysis. So principal component analysis and PCA full using Excel and cumulative like this. So we get the evaluating the PCA performance. So this plot helps decide the number of components to return for achieving a desired variance threshold, right? So you get the number of principal components, and you get the cumulative explained variance. So it's like this, and then we get the conclusion. So principal component analysis simplify high-dimensional dataset while preserving most information. So explain variance ratio guides the selection of principal components. Visualizing principal component analysis transform data, refer patterns, and separation in classes. So you can see that this is the classes in the separation principal component. Right, so this is pretty simple using principal component analysis. Maybe we want to check the example case. So example information in real data. Maybe in here we check this. So statistical producer that informs the manual. example as per maybe just in here, like this. So this is the principal component analysis. It's a technique used to analyze data by reducing its dimensionality. It can be used in many fields, including image compression, data visualization, and anomaly detection. So this is the example cases in principal component analysis. So our example is using data wine, right? So this is the clustering of the wine data. But what if you have a real data or real problem that you want to solve? So this is the example of the using principal component analysis. The first one is like image compression. So principal component analysis can compress image while keeping the most important information. This makes image easier to store and share. So they reducing its dimensionality. So but while keeping the most important information. And data visualization, principal component analysis can help visualize data by projecting it into a lower dimensional space, such as 2D or 3D plot. This can make it easier to understand and explore the data. So you can use an anomaly detection, which can be used to find unusual data points, such as those in credit card transaction, sensor reading, or network traffic. Also, there's a financial service. PCA can help analyze large amount of financial data, such as portfolio of securities. It can simplify the problem by extracting the most important component of the data. Also, there's a classification accuracy. PCA can be used to improve the accuracy of machine learning model. For example, PCA can be used to reduce the number of features in a model, which can improve accuracy. Also, there's a noise filtering. PCA can remove noise or redundant information from data. For example, PCA can be used to remove noise from data that is spread out along one axis but has a lot of along another axis. So this is the example of using PCA. So there's a lot of useful case, or there's a lot of case using principal component analysis. This is the one of the powerful machine learning concept in machine learning. So you have to understand the meaning and you have to understand the concept. So you make this, because in real data have a lot of variable features, like a lot of x, but you want maybe just compress them into just 2 or 3, but doesn't lose its meanings to all of the variable x. I think that's the concept that you have to understand. Okay guys, I think it's for the principal component analysis. I will learn and understand what's the useful of principal component analysis, because this is so much useful in statistical and machine learning technique. Okay guys, thank you for watching. See you guys in the next video. Thank you. Hello, welcome back guys in this section unsupervised learning, dimensionality, reduction. So in this subsection 2 is tSNE, like tDistributed Stochastic Neighbor Embedding. So the tSNE is a dimensionality reduction technique specifically designed for visualizing high dimensional data in 2D or 3D space. Unlike principal component analysis, which focus on maximizing variance, tSNE emphasizes preserving the local structure of the data. So the key concept is preserving local similarity, like tDistributed Stochastic Neighbor Embeddings maps similar data points closer together in low dimensional space. It's like non-linear reduction. It captures non-linear relationship in the data. So in hyperparameters like perplexity, control the number of nearest neighbor used during computation. Learning rate so determines the step size during optimization, and iteration, number of optimization steps. So the first one, we want to importing library and datasets. So we will use the MNIST dataset, a collection of handwriting digits for this demonstration. It is high dimensional dataset, ideal for visualization using tSNE. So if you don't know what is MNIST dataset, so we want to check in here MNIST dataset. So MNIST dataset is like this. So this is the MNIST dataset. It's collection of handwriting digits, right? So MNIST dataset is in here like this. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8. So MNIST dataset is like this. So they detect the number of the image. So this is one of the popular data in machine learning. So yeah, you want to use this data for the our tSNE tDistributed stochastic neighbor embedding, right? So we want to use the MNIST dataset. So we want to check it in here first. So in here we want to use the subsection. So we will use the MNIST dataset, right? So the datasets contain 64 features x times x pixel value for each image and 10 classes digits. So the MNIST dataset looks like this, right? So this is the 0 until 8 times 8, right? So this is the pixel of the MNIST dataset. So 0, 0 in this row, and 0 until 7 again. So this is x times x. So you can see like the dataset contains 64 features, like this 64x. So the x is 8 times 8 pixel value for each image, and 10 classes, which is the digits is 0 until 9, right? So there's MNIST dataset. So x times x data. So this is the feature, like this is the first feature, second, like something like this. So 4, 4, 4 is like same color, and then this is 4 same color, and then this is 5. This is 5 same color. So this is the where is it? 10 and 14 and 10 again, 10, 12, like this. So this is the sklearn's data example. So yeah, we use this data for MNIST dataset. Next, we want to data pre-processing. So before applying tSNE, features needs to be standardized to ensure all the dimensions contribute equally. So like usual, we want to standardize the data. So this is usual standardized data. So we want to applying the tSNE, and we want to visualization the tSNE result. Right, so next we want to applying the in here. So we reduce the dataset to 2D for visualization. Key parameter like perspectivity and running lag can be tuned for optimal result. So we use apply tSNE like this. So the library of tSNE is using sklearn manifold. So import tSNE in here. Right, so we use this as the library of using tSNE, and you want to check the components too. Property is 13, like learning rate 200, and insurance. This is the can be tuned for optimal result. So this is just an format for the the basic numbers. So we just use this and using the tSNE and fetch transform x scale, and then we use data convert result to data frames using tSNE, like using two component array. So this is the columns dim1 and dim2, like the target is y. So we use check in here, like this is almost same concept in principal component analysis. So the principal component analysis is using PC1 and PC2, right? So we will this before. So but in the principal component analysis, we mix the certain features into 2 or 3 dimension. In our tSNE, we use 64 and then we reduce them into the 2 component like this. And we want to check the position of the tSNE. So visualization the tSNE result. So we visualize the 2D representation of the dataset to observe clustering patterns, right? So we use GIM1 and GIM2 target, and we use tSNE visualization of MNIST dataset. So each cluster represents a digit with similar digits placed closer together. For example, 1 and 7 may overlap due to similar shape. So we can see in here, and 7 is gray. Where's the gray in here? Like 1 is in here. So it may be some of them may be overlap due to similar shape, but I think it looks good in here. So this is the 9, this is the 3, this is the 2, and this 8, this is 1, 1, maybe some overlap in 4, and this is 4, this is, but there's a 2 in here, I don't know why in here, and this is 0, 0 is cluster, the perfect cluster in here, and this is 6, but there's a 5 in here. So yeah, this is cluster represents digits in the y variable. Next, we want to check the tuning hyperparameter. So adjusting hyperparameter can significantly impact the tNE result. Experiments with different value of perspectivity and learning rate to achieve better separating of cluster. So the tuning hyperparameter, we want to check the perplexity, and we see in here we use perplexity is 13, right? So but we want to check is 5, 30, and 50, which one is much better if using different perplexity. So you can see in here, so this is the first using perplexity is 5. So so while we wait, we want to check in here, and so this is the tSNE with perceptivity is 5, like this. So this is 30, and this is 15. Yeah, it's not much of a difference between some of them, but you can see that, yeah, maybe not too much different, but I think the 13 is much better because some of them not overlap, like this is overlap, this is the much overlap in here, but in the 13 is not really overlap. So there's overlap but not too much like this, and if we see this too much overlap, this is the too much overlap. In here there's too much overlap, so yeah, maybe the 13 is much better than the 15 or the 5, right? So we can check. So difference possibility value adjust the balance between local and global structure in the data. So we want to check maybe the average student score is 0.11. So tSNE effective visualize high dimensional data by preserving local relationship. Perplexity and learning rate are critical hyperparameter for meaningful results. So we use this perplexity, right? So how about the learning rate? We change like 200, 100, or maybe 500, and then in ether we want to check the hyperparameter also. So this is the call. Its name is tuning hyperparameter. So we make a difference hyperparameter value, right? So maybe we want to adding the learning rate, so different learning rate, a different iteration or something like that. So yeah, this effectively high visuals high dimensional data by perspective local relationship and proficiency and learning rate are critical hyperparameter for meaningful results. So maybe proficiency and learning rate we can check a difference value, and visualization provide insight into data cluster and relationship. So I want to highlight like what is the difference using tSNE and PCA, right? So if you are wondering too, so what is the difference between using TNA and PCA, right? So we can check in here. tSNE and PCA are both algorithms that can reduce the dimension of high-dimensional data. They differ in how they preserve data structure, their algorithm types, and their effectiveness in capturing global or local structure. So the tSNE is prefer local relationship between the data points, but PCA preserve the global structure of the data. So the tSNE is stochastic, so meaning that rerunning it can produce different results. So this is important because if we are running, it can produce different results. So because they stochastic, but PCA is deterministic, meaning that running it twice on the same data set will always produce the same results. So global and local structure capture, tSNE excel at capturing complex nonlinear structure, and PCA effective for capturing global structure, especially when there is a linear relationship between the features. So other difference is tSNE is less sensitive to the ordering of data points. tSNE is a good algorithm for visualizing complex high-dimensional data, and PCA is more computationally efficient. So this the difference about using PCA and tSNE. So maybe we want to check the example. So yeah, it's really same what we learned earlier. So this is MNIST PCA. So this is MNIST tSNE. So yeah, it's much difference using PCA and tSNE, right? So yeah, this is the same concept that PCA deterministic and this is stochastic. This is a linear and non-linear, global and local. Okay, I think it's for the tSNE, and you can learn about it more later. So yeah, don't forget to tuning the hyperparameter for the best tSNE, and tSNE is stochastic, meaning that if we run again, it will not generate the same value, right? So PCA is deterministic, meaning that we run again, it's literally just same value. Okay, guys, I think it's for the tSNE, tDistributed Stochastic Neighbor Embedding. So thank you for watching. I will see you guys in the next video. Thank you. Okay, welcome back guys. So in this section, unsupervised learning, dimensionality reduction, we go to the next is autoencoder. So autoencoder are a type of neural network so used for unsupervised learning. They are designed to learn efficient representation and encodings of input data, making them a powerful tool for dimensionality reduction. So in here, so the autoencoder consists of two parts: an encoder that compress the input into a latent space representation, and a decoder that reconstruct the input from this representation. So last function, like autoencoders, minimize the reconstruction error, which measure the difference between the input and the reconstruct output. So the application is dimensionality reduction, anomaly detection, image denoising, and etc. So we want to check this in autoencoder. So autoencoder, sorry, um, autoencoder like this. What is autoencoder? So you want to so autoencoder is a neural network that compresses and reconstructs data. It's a type of unsupervised machine learning that learns to identify the most important features of input data. So how it works? So autoencoders learns to compress input data into a lower dimensional representation called the latent space. So autoencoders is learn to reconstruct the original input data from the latent space. So data compression, like autoencoder, are used to compress data for storage or transmission. So like what is used for like image denoising, like autoencoder can remove noise from image, anomaly detection, facial recognition, generative text. So this is the autoencoder looks like, right? So this is they use encoder and they use a decoder. So if you learn again in here, so an autoencoder consists of two parts: an encoder that compresses the input into a latent space representation, and a decoder that reconstructs the input from this representation. So this is the original, they encode, and this is the compressed representation, and then decode, and then this is the reconstruct input. So this is the example of the encoder and decoder. So this is the input image, so they encode the data, and then this is the bottleneck, so latent space representation, and then they decode, right? So this is the reconstruct image. So this is the more example using this is the input, this is the output, right? So it's like and something like this. So this is the input. Maybe this is much like it. So they have a latent space representation and they decode. The output is much more good. So this is one of the example. So this is the corrupts image. So they choose the inputs to in the encoder, and then the decoder is reconstruction loss against original image. So yeah, it's like that. We go back in here. So we check the autoencoder. So this is so what is used for image denoising, like can remove noise from image. So anomaly detection, can identify unusual data points, facial recognition, can identify face in image, generative text. Some autoencoder can generate new data like image or time series data. This is the type of an autoencoder like variational autoencoder, adversarial autoencoders, and concrete autoencoders. So we go to our EMS dataset. We import the dataset like usual. and then we building the encoder, building the autoencoder. So in here we make a text. Autoencoder. Step 1 is we will import again the dataset, MNIST dataset. So MNIST dataset handwriting digits demonstrate autoencoder for dimensionality reduction. So the MNIST dataset is normalized to values between 0 and 1 and received into 2D array for input the neural network, right? So we check the data, so we use datasets import MNIST, but we use the TensorFlow Keras dataset. So MNIST dataset, this is our training and testing data. So before we use the data MNIST using this is like sklearn datasets and load digits. So load digit we use the data MNIST, right? So in here we use TensorFlow. So this is one of the most popular in machine learning. So maybe we want to check this. What is TensorFlow? So Keras, maybe we want to TensorFlow first. So TensorFlow is an open source library that helps developers build and deploy machine learning applications. It's used by data scientists, software developers, and educators. What does TensorFlow do? Trains and run deep neural networks, help with data acquisition, serve prediction at scale, refine future results, and help with statistical and predictive analytics. So what can TensorFlow use for? So this is the natural language processing, image recognition. So MNIST actually handwriting recognition, right, and image recognition. So that's why we use TensorFlow. There's a computational-based simulation, object detection, MRI, image processing, fraud detection, and self-driving car. So how does TensorFlow work? So use data flow graphs where nodes represents mathematical operation and edges represent multidimensional data arrays. Tensor. So use auto differentiation to automatically calculate the gradient vector of a model. How is TensorFlow used? I use thousands of company, right? So use an GPU or GPUs, or you can use tensor processing unit designed by Google. And then we want to Keras. So Keras is the high-level API of the TensorFlow platform. It provides an approachable, highly productive interface for solving machine learning problems. With a focus on modern deep learning, Keras covers every step of the machine learning workflow, from data processing to hyperparameter tuning to deployment. So maybe we want to check this. So this is one of the best data and was the best library. The library in the Python machine learning. So yeah, you should know this, and yeah, if you want to use this, is much more powerful than other library that we use for. So in our example is we use TensorFlow, Keras, and we use models, layers, datasets, MNIST, and we want to use optimizers, and we will use the Adam optimizer. We will get this later, but and our dataset is it is a 17,000 data. And MNIST dataset is normalized to value between 0 and 1 and received into 2D array for input into the neural network. So this is the MNIST datasets, and we want to normalize and flatten the data. So we flat the data because RGB. So this is a 55. So we want to extrain, and retraining the data is 16,000, and the test is 10,000. And then the step 2, we will building the autoencoder. So building the autoencoder, we define a simple autoencoder with an encoder and decoder, right? So input, extract step, we define the dimension like encoding dims, reduce dimension. Like we use encoder in here like input, and then we use decoder, and activation is ReLU and sigmoid. So this is one of the statistic that we use at the machine learning, but this is much more the equation. And so if you are beginner, you will not really understand what is this mean, but you should know that this is one of the something like this. So this is the activation function. Like we use ReLU, and there's a sigmoid, and then the time, and then the ReLU, and max out, and LU. So this is just equation. So I will not get this more, but we just using the Python code, right? So we just using the activation, activation. We use a model, input layer, encoder, and we compile the autoencoder. So we will check the autoencoder. Right? So the encoder compress the input into a latent space of 64 dimension, while the decoder reconstruct the input from this latent space. So we will input the layer, and this is the parameter. So we want to next is training the autoencoder. We want to train the autoencoder using the training data and validate it on the test data. We want to use in here. So training, we train the autoencoder using the training data and validate on the test data. So we use epochs and batch size, right? So if you want to see like epochs is this. Okay, I will tell you while we wait. I will tell you about epoch like this. So epochs in machine learning. So you have batch size is 1000, right? So this is iteration per epochs. But if you have maybe 5 epochs, so you want to difference them, so the data is running simultaneously, right? So epoch in neural network. So this is an epoch in neural network is the number of times the entire training dataset is passed through the neural network. So it's fundamental part of the training process for machine learning algorithm. So during training, the model learns from its example in the datasets. Weight and bias, the model adjusts its weights and bias to improve its accuracy with each pass. And also there's hyperparameter. The number of epoch is a hyperparameter, which means it's parameter that sets before training begins. And then the batch size, the number of training sample used one iteration of the training process. So the right number of it is important for the model to run effectively without overfitting. The number of epoch is often set to large numbers, such as thousands, to allow the algorithm enough time to manage any errors. So techniques like early stopping can be used to prevent overfitting by stopping training when the model performance on a validation set starts to degrade. So the neural terminology, one epoch is one forward pass and one back pass for all the training example. And batch size, the number of training example in one forward or backward pass, the higher the batch size and the more memory space you will need. So this is the epoch. So we have a lot of data, right? So we have 16,000 data, but we want to use them. So we want to like difference them like this. There's iteration per epoch. So yeah, they use them as an like batch size like this. So this is the iteration per epoch. So yeah. So while we wait, so this is our validation, and this is you have to see the file loss and file loss, and this is the lower something like this, that is lower. And there's a theory where like when loss and file loss happen when overfitting. So overfitting is generally indicated by the training loss decreasing further, but with the validation loss starting to increase at some point. So the validation loss starting to increase at some points. So this is the overfitting. So we can see the file loss is under and not increasing, but they decreasing like this, decreasing. We can check 31, 29, 27, and this is not increasing. So our model is good. So this is the where our model is overfitting, right? So this is the 7 to 3 and this is the 7 to 4. So this is where the overfittings comes. So the overfittings means like with the validation loss starting to increase at some points, right? So yeah, this is indicate that our data is overfitting. That is how they always they decrease the loss, decrease the file loss, but at some point it will go to it will increase the validation loss, but yeah, it becomes overfitting. So that is the concept of overfitting using file loss. But this is not really increasing that much, so we not really concerned this about this in overfitting. So it's all good in here, but at some point maybe there's a lot of increasing, so that was the overfitting, but this is not really increasing that much, so we should not too much worry about that. Next, we want to check the visualization, the encoded representation. So after training, we use the encoder to transform the data into a lower dimensional space and visualization. So we want to encode the data and we want to visualize the encoded representation. So the encoded representation show the data in reduced dimensional space. Cluster may correspond to similar degrees. So this is the encoded data MNIST dataset. This is same encoded using in we can see in Google, right? So this is the encoded represents MNIST dataset. So we want to evaluating the recurrent certain quality. So yeah, this is the original and the MNIST dataset. So you can see that we reconstruct the test data and we visualize original vs reconstruct image. So this is and we want to 10 number display. So we want to check the original and we recurse the data. So this is almost same original and recursive data. So this is the encode and we decode again, right? So this is the original input and this is the reconstruct. So this is the original, this is the reconstruct, this is the original one, and this is the reconstruct. So this is an example using encoded and decode, right? So if we want to make conclusion in here, so autoencoders effectively reduce dimensionality by learning compressed representation of the data. So reconstruct quality indicate how well the reduced representation retain information. Encoded representation can be used for clustering, anomaly detection, or as a feature for other model. So this is one of the most using model in the real world, so like anomaly, clustering, or another. So this is a good example using MNIST dataset. So MNIST dataset is one of the data that popular. So MNIST dataset, one of popular data. Dimensionality is popular and widely used dataset in the field of machine learning and computer vision. It stands for Modified National Institute of Standard and Technology and consists a large collection of handwriting digits. So this is the MNIST dataset, handwriting digit. So this is one of the most popular data that machine learning basics. So if you new in here, so it's okay. So we use this data. Okay guys, I think it's for the autoencoder. I hope you understand the basic of encode and decode, and we want to using the encoded dimension, and we check this as a train to encoder. So we use also encoder and fit the X train, and epochs is 15 and batches is 24 256. We shuffle them, and then validation is X test, right? So we use autoencoder in here. We check the model. So yeah, so autoencoder we use a model in here, model using input. So we use the 10 for flow, class, and model. So we import model like that. So guys, I think it's for the autoencoder. Thank you guys for watching. I will see you guys in the next video. Thank you. Hello, welcome back guys. So this is our last section in the subsection 7, unsupervised learning, dimensionality reduction. So we go to our project, visualizing wine data using PCA and tSNE. So the goal of this project is to apply dimensionality reduction techniques, so namely principal component analysis and tDistributed stochastic neighbor embeddings to the wine dataset. We will visualize the data in a lower dimensional space to explore patterns and relationships. So we importing the library and the data sets. So the ones data. So we wants to pre-processing, and we make in here maybe projects. So like usual, we want to import the wine data. We want to check these certain features, right? So describing one characteristic and 3 target classes, and we want to check. We want to data pre-processing. So standardizing features ensure that all dimensions contribute equally to the analysis. like this, and we want to applying PCA, and we want to applying tSNE, and we want to compare them, right? So this is a comparing between PCA and tSNE. So in here we want to applying PCA, and we want to applying tSNE. So the PCA is we use PCA to reduce the datasets to 2 dimensions for visualization while returning as much variance as possible. So with PC1 and PC2, we want to use a variance ratio, and we want to use PCA visualization of one datasets, like one class in here. We want to check the applying tSNE with tSNE to capture nonlinear relationship in the data for more detailed visualization. We use the n components 2, perspective is 13, learning rate is 200, and iteration is 1000. And then we convert tSNE result to data frames, and the target is y, and then scatter plot we want to dim1 and dim2 like tSNE visualization of one dataset. Dimension 1 and dimension 2 like this. So this is the one class using the tSNE. So we want to check which better, right? So we want to comparing the PCA and tSNE. So this is the PCA visualization like this. So we overlay PCA and tSNE results to analyze their clustering effectiveness. So compare PCA tSNE in subplot. Like we use principal component 1 and principal component 2, and we use a dimension 1 and dimension 2 like for tSNE visualization. This is use a one class for the PCA and tSNE, right? So the target is 0 in here and cluster here, and 1 in here and 2 in here, but in PCA visualization in here, right? So we want to comparing them, and then we want to make maybe we delete this. So the PCA highlights variance in the dataset but may struggle with nonlinear relationship. So but tSNE capture nonlinear relationship and provide a more detailed clustering. Both techniques complement each other in exported high-dimensional data. So actually there's no one much better and then the others, but we want to check the two of them. So and then based on the data like usual, right? So this is the example project using wine data using model PCA and tSNE. But we already told you the difference about PCA and tSNE, so maybe we want to check again difference between. So maybe we want to which one better, or tSNE. So this is PCA and tSNE are both dimensional reduction tools that are effective in different situations. PCA is better for linear data, while tSNE is better for non-linear data. So this is the key of the concept. So PCA is best for linear data, feature extraction, and exploratory data analysis. How it works: so maximize variance in the data. Advantage is computationally efficient, and descendant may lose information from the original data. So tSNE is best for non-linear data, visualization complex data, and revealing cluster. how it works. So keep similar data points together and dissimilar data points apart. An advantage is preserve relationship between data points. So this advantage is computationally expensive and may not work well for large data set. So when to use is PCA good for exploratory data analysis and pre-processing, and tSNE is good for creating visualization that highlight cluster and relationship. So if you want to use PCA is for exploratory data analysis and pre-processing, but tSNE good for creating visualization that highlight cluster and relationship. So it's maybe you want to check this stack. So maybe whereas PCA is more simple than tSNE, tSNE is a great piece of machine learning. And then but one can find many reasons to use PCA instead of it. One of top of my head, I will mention 5 as most of the other computer science model in use. tSNE is no silver bullet, but there are quite few reasons that make optimal choice in some cases. Let me mention some of Venus brief. So stochastically of final solution, PCA is deterministic, TSA is not. Interpretability of mappings. This is the above point presume that the team has agreed in pattern random set run. So this is more advanced of why the PCA much more better than the tSNE, right? So this is another things using the same block. Yeah. Okay, I think it's for the example for PCA or tSNE and the differences outputs because in them. So, okay guys, thank you for watching. I will see you guys in the next section. Thank you.